Hello everyone. Recently, when I was browsing eBay, I found all kinds of metal detectors, from professional devices that cost several tens of dollars to a DIY module that is only about $3. I was curious to know if something that cheap could really work, and how its mechanism actually operates. So I decided to buy a kit and assemble it myself to try it out. Inside the box, there is a printed circuit board and a few separate components. Now I will try soldering and assembling it into a small metal detector, then test if it can really detect metal, and after that let's explore how it works together. Oh, it actually works. At first, I needed to turn the variable resistor a little to adjust it, so that the beeping sound completely stopped. After that, when I tested it with some metal objects, the detection distance was only about 2 centimeters for small items and around 5 centimeters for larger ones. Even though the sensitivity is not very high, for such a cheap kit, it is still quite interesting. Now let's take a look at how the circuit inside actually works. This is the circuit diagram provided by the manufacturer. In general, it only uses very basic components such as resistors, capacitors, inductors, a transistor, and a buzzer. If we look closely, we can roughly divide the circuit into 3 parts. Part 1, the oscillator circuit. Part 2, the amplifier and signal processing section when changes occur. Part 3, the alarm section with a buzzer, or LED. First, let's take a look at the oscillator, the heart of this metal detector circuit. You can see in this circuit, there is only a single signal taken from the collector pin of transistor Q1. When measured with an oscilloscope, the signal appears as a sine wave oscillating at a frequency of about 260 kHz. So why does the circuit oscillate? Let's look at a simple LC circuit made of a capacitor, an inductor, and a switch. At first, the capacitor is charged. Then we flip the switch to connect it to the inductor. The capacitor discharges, creating a current through the coil and forming a magnetic field. When the capacitor is empty, the magnetic field collapses, generating a reverse current that recharges the capacitor. Energy keeps exchanging back and forth, creating oscillation. But in reality, there are always losses, so the oscillation will gradually weaken and stop. To maintain the oscillation, we need to add a transistor to amplify and feed energy back into the circuit. Now, instead of a switch, we use a transistor to turn on and off. Add a second inductor, L2, wound close to the main inductor to pick up the signal. This signal goes through a capacitor and then into the base of the transistor. The capacitor blocks direct current and only allows the alternating signal to pass through. Next, a 200 kilo ohm resistor is connected to the base to provide bias current, helping the transistor start conducting. With these basic components, the circuit can already oscillate by itself and maintain continuous oscillation. More specifically, when power is applied to the circuit, the current through resistor R1 creates a small bias current at the base, making the transistor ready to conduct but not strong enough to operate fully. At the beginning, capacitor C2 is not charged, so it allows current to flow through the L2C2 branch into the base, causing the transistor to conduct. When the transistor conducts, capacitor C1 charges quickly. After C1 is fully charged, it begins to discharge through inductor L1, creating a changing magnetic field. This magnetic field induces a voltage into coil L2, producing a reverse voltage across capacitor C2 and continuing to drive the transistor. When C1 is fully discharged, the magnetic field in L1 collapses, again inducing a new signal in L2 that is fed into the base. This cycle repeats continuously. In other words, C1 and L1 form an LC resonant circuit, while the transistor, together with the L2C2 pair, acts as an amplifier and provides positive feedback. As a result, the energy lost in the LC oscillation is always replenished, allowing the oscillation to be maintained stably. At the collector of the transistor, we obtain a stable sine wave signal, which can be clearly observed on the oscilloscope. This is the circuit I have soldered according to the schematic. For the L2 coil, I only needed to wind a single turn around the main coil to get the feedback signal. When measured, the circuit outputs a fairly stable sine wave at the collector of the transistor, exactly as the principle we have just analyzed. We already know how the oscillator works, but how can it detect metal? When we bring a piece of metal close to the L1 coil, we can see the oscillation amplitude decrease. If the metal object is larger and placed closer, the oscillation signal may even be completely suppressed. The principle here is that when metal is near the coil, the changing magnetic field induces eddy currents inside the metal object. These currents dissipate energy, acting like an extra resistor in parallel with the coil, which makes the oscillation quickly weaken. In other words, the metal absorbs part of the resonant circuit's energy, causing the signal amplitude to drop significantly. The sine wave oscillation from the LC circuit is fed into transistor Q2, causing Q2 to switch on and off continuously according to the oscillation. Capacitor C4 is connected to the collector of Q2. When Q2 conducts, the voltage on C4 is pulled down close to VCC. When Q2 is off, resistor R2 pulls it back up near GND. As a result, the original sine signal after Q2 is no longer a pure sine wave, but becomes a distorted waveform, with the on and off times not symmetrical. When the amplitude of the LC oscillation decreases because metal is brought near, the on time of Q2 becomes shorter than the off time. As a result, the voltage on C4 shifts more toward GND. This change makes transistor Q3 conduct, supplying current to the buzzer and the LED. This is how the circuit detects metal and generates the alert signal. In general, this circuit can detect metal, but its major drawback is that the output signal is not accurately proportional to the size or density of the metal. This limitation is quite common in low-cost circuits. In the next video, I will try to develop an improved version with higher sensitivity and better accuracy. If you are interested, make sure to stay tuned. And if you found this video helpful, don't forget to hit like, subscribe to the channel, and leave a comment to give me more motivation to make the next videos.